So here's the three topics that we're gonna cover today. In the first topic, we'll discuss about the definition of beam and beam support. For describing the bending of beam properly. Okay, so after defining the beam, because the topic and the name of the chapter is like analysis and design of beams for bending, we'll first define what is beam, and then we'll talk about like external forces and torque that induce the bending of the beam. And even though when we add some external forces, there must be support. Like without any support, it will be simply a dynamic problem, right? So to make a static problem, yeah, we have to have some beam support, and that's the first topic we're gonna do in today's lecture. And in the second topic of today's lecture, we'll discuss about shear moment diagram. Yeah, even though I use a fancy word, shear moment diagram, and what you're gonna do is simply we'll obtain shear force V and moment M as a function of position. That's it. That's what shear moment diagram refers to. And as a third topic, we'll discuss about the relationship between shear force V and shear moment M. Okay, so let's start from the first topic, beam and beam support. So let's begin from the definition of beam. Like beams are long and thin structured members supporting transverse loads and or moments orthogonal to the long axis. Here, the long axis refers to this x-axis, which is parallel to like a long axis of the beam. Okay, and as you can see, beam typically refers to long and thin structural members. And what you can see here is there can be two types of transverse load. First transverse load is distributed loading. You apply a distributed loading like uniformly or non-uniformly in specific region of the beam. And you can also think about transverse point load as an external loading, which can induce the bending of the beam. And regarding the moment, if you think about the right hand rule for this moment, the vector will heading to the direction out of this plane, and direction out of this plane would be orthogonal to long axis as the definition of the beams. Okay, so these three loadings, distributed loading, point force, and the the moment, will be three types of loading that we're gonna consider in chapter 5 and chapter 6. After we discuss about three types of the loading, we'll discuss about three types of support that makes the beam bending problem as a statics problem, like without any external support, unless you make a really careful arrangement of external loadings, and your structure will be will not gonna stay in mechanical equilibrium, right? But if you have some sort of support, then it's quite easy to like design like a statics problem, right? Bending beam under bending without any motion, right? So the types of support that we're going to consider in our textbook are as follows. First, we'll consider cantilevered beam, and typically you're going to see these kind of diagram. This is rigid wall, and this refers to cantilevered beam boundary condition. Even though textbook and I make this kind of diagram, it has mathematical meaning. So when you see these kind of visualization, it means that angle dy dx, y is the displacement in vertical direction. The dy dx refers to this is the slope is dy dx. Okay, this is x and this is y. Then this angle stays as exactly 0 at this boundary, and the position stays also as 0. Okay, so no displacement in vertical direction. Okay, that's what this visualization, cantilevered beam visualization means. And second, you're gonna see simply supported beam. Okay, instead of having these kind of rigid wall, you're gonna have visualization of a little triangle. One triangle will have like a rigid wall like bottom here, and the other triangle will have like a circle or wheel in the bottom. This refers to there will be no force along the x direction, so you don't need to worry about x direction because the x directional force will be released by this freely rotating wheel, and that's what this diagram means. And the mathematical meaning at these two ends are only position y equals 0 is fixed, and there is no constraint on angle. The only constraint is on the moment at both sides. And if you look at this problem physically, to have this local moment m, what you need is you need compression on the upper part, you need tension in the down part, you need a sort of wall, right? But in the absence of any side wall, physically you cannot hold any moment or any local torque that give rise to these kind of torque direction. Okay, so when somebody say like one boundary is simply supported beam, it means only position is fixed and moment is fixed as 0. Okay, and as a third beam support, you're gonna encounter hinge support. In hinge support, it means you can see that there is no side wall, so it visually means that m must be 0 due to the free rotation. Here this is O shape means free rotation, and because there is no side wall, m must be 0. Okay, that's the what this hinge visualization means, and neither angle nor position is fixed when you encounter hinge. Okay, so given this three types of force, and given 1, 2, 3 types of bending support, your job is first, from the statics or from the freshman physics, you obtain a moment and shear force distribution as a function of position, and second, out of moment and shear force V, you obtain the distribution of normal stress and shear stress along the position of the beam. That's what you're gonna do for the reliable design of the beam under the bending. Okay, so even though we discussed about bending in chapter 4, in chapter 4 we limited our focus in pure bending, which is only m is non-zero and n, t, and v are 0 cases. Here we started to discuss more general bending phenomena. Okay, so with that, let me finalize my video lecture on first topic of today.